Hello wonderful person, this is Anton, and today we're going to discuss a somewhat intriguing explanation for a lot of different cosmological mysteries that has potentially now been kind of disproven. In other words, it took just a couple of weeks for someone to disprove one of the most exciting explanations in cosmology in the last few years. But in order to understand what's going on here, let's first imagine this. Imagine you're looking at a giant piece of cloth. And well, if you look very closely at the fibers, you'll usually see knots and gaps that are hidden inside. But if you zoom out far enough, this cloth looks completely smooth and uniform. And well, for decades, when it comes to understanding the universe, this was pretty much our fundamental view. This is known as the cosmological principle, and it essentially assumes that on an extremely large scale, the universe is homogeneous. It's the same everywhere, and it resembles this fabric no matter where you go, while also being isotropic, or basically being the same in every single direction. So in other words, it's as if this fabric was basically the same everywhere you go, and also appears to look the same no matter what direction you look from. But what if that particular foundation was incorrect? What if this cloth or this fabric is actually kind of stringy and uneven, and basically contains some unusual deformations and some unusual unique clumps that are just invisible from a distance? Or basically something that's very difficult to see on a large scale, but seems to be there if you look much closer. And that's essentially what one of the recent studies proposed. A study by Francesco Labini and Marco Galoppo in a prestigious Nature magazine proposed a few things that, in theory, could append everything we know about cosmology. And exactly what they proposed we're going to discuss in approximately 1 minute. Because, as it often happens in science, an extraordinary claim requires extraordinary evidence. Copyright Carl Sagan. Because a follow-up analysis and a study that was just released a few days ago has now presented us with a really exciting lesson in how we measure cosmos. And so let's discuss these ideas of cosmological principle in a bit more detail, and discuss how, apparently, misunderstanding cosmic distances can sometimes create a lot of confusion. But to understand everything here, let's start with the basic model referred to as lambda CDM, the current recipe for the universe. Here, this model suggests that the universe is made out of 5% ordinary matter, or basically stuff that you see around you, 27% dark matter, and 68% dark energy, with the word dark in this case referring to the fact that we don't really know what it's made out of. And here this model predicts that while we see a cosmic web of filaments, walls, and voids on much smaller scales, all of these structures should technically fade away once you start looking at a much larger scale, involving distances of hundreds of millions of light years. And so, for example, think of the Hubble's law. We know galaxies are moving away from us at the speed proportional to the distance, because we believe the universe is expanding away from us at a relatively uniform rate away from planet Earth, meaning that there is no actual up, down, left, or right in space, and everything is pretty much the same in every direction. And this simplicity is important for this idea of cosmological principle, because it basically reduces 10 very complex equations of gravity, into just 2, making the whole math of the universe actually solvable. But then we have this bold new claim. In June of 2026, astronomers that were using the data from Dark Energy Spectroscopic Instrument, the instrument often referred to as DESI that we've discussed in some of the videos in the description, and the instrument that mapped tens of millions of galaxies in the last few years, decided to test this idea. And so here, Dr. Labini and Dr. Galoppo applied a new statistical tool to all of these previously discussed maps. But instead of just asking how likely it is to find a galaxy at a certain distance, they measured how the distribution of galaxies varied with both distance and angle. And here they reported finding coherent anisotropic features, or basically discovered that there is a kind of a preferred direction for certain galaxies to appear, while also discovering these massive string-like structures expanding to billions of light years in scale, or about 10 times larger compared to what we usually assume when it comes to the cosmic web, and some of the largest structures in the universe. Or essentially they suggested that the universe was not smooth on a large scale, and was basically kind of stringy and kind of textured. And well, if this were true, this would be groundbreaking. As a matter of fact, some scientists that read the study even suggested that in theory, this could then eliminate the idea for dark energy, explaining the acceleration of the universe as a kind of a feedback effect from these giant imbalances in matter. So I guess in theory, this could have solved at least one major mystery in cosmology right away. But going back to Carl Sagan, so, basically, prove it, bro. And the rebuttal in this case did not take very long, came from a single researcher, and is actually just a little bit embarrassing, because in this case, it might have been the units of measurement. And so in this recent publication by Till Sawala from University of Helsinki, the one that just came out a few days ago from when I'm making this video, here the researcher noticed that something was off basically right away. He actually decided to re-examine the same DESI data, discovering a major discrepancy. And basically here this was not a flaw with our understanding of the universe, but rather a subtle error in how the cosmic distances were calculated. And that's because in cosmology there are at least two major ways to define distance. First, there is something referred to as luminosity distance. This is based on how bright or how dim an object appears. But then there is also something referred to as co-moving distance, with this distance accounting for the expansion of the universe and effectively keeping the ruler consistent as the space grows. So I know it's kind of confusing, but one of the more common explanations here basically involves this analogy involving a raisin bread being baked. And so here, imagine that each of these raisins is some kind of a galaxy, and as the universe expands, the distance between these individual galaxies grows as well, and so that's your co-moving distance. And well, in this case, Sawala's analysis revealed that the original study in the Nature magazine mistakenly treated luminosity distances as if they were co-moving distances, which not surprisingly caused a dramatic enlargement in data and essentially resulted in a major error. Okay, I know this might be just a little bit confusing, so let's try to use a different analogy to try to understand the difference between co-moving distance and luminosity distance. So for co-moving distance, once again, this is probably the best example. So here we have a loaf of bread that's expanding over time, and as these galaxies or these raisins move apart from each other, the measurement expands the space between them as well. And so the co-moving distance tells us how far away two galaxies are if you basically pause the expansion of the universe right now. But in luminosity distance measurements, it's not actually about space, it is about light, luminosity. And so imagine some kind of a star as a light bulb. If you know how bright it should be, or its actual luminosity, by looking at it from far away and by discovering how much dimmer it is, you can then estimate the distance. But because the universe is expanding and the light travels through the space that's stretching, the stretching creates redshift and basically makes the light appear just a little bit dimmer than it would be in a static universe. And so if the universe is not changing, the star is going to appear much farther away. But because of this expansion, it just starts to appear a little bit more faint than it truly is. In other words, just to kind of summarize this, the co-moving distance essentially tells us how far away something is on the map, whereas the luminosity distance tells us how far away the object appears based on how bright it is. And it's really this that was a mistake in the study. Here, the error factor changes with the redshift and doesn't just make things look bigger, it even warps and deforms the shapes of the structures in the process. So for example, one structure that's very famous, the Sloan Great Wall structure, one of the largest structures in the universe, appeared significantly enlarged and distorted in the original study's map. But when Dr. Sawala used the correct coordinates, specifically correct co-moving coordinates, these gigaparsec structures vanished, and all of the galaxies were right where the standard model predicted them to be. And on top of this, there was another issue, specifically how the data in the study was compared to simulations. The original study compared the DESI data, or the dark energy data, to a simulation made out of simple dark matter particles. But galaxies are not random particles and do actually have a bit of a bias. Specifically, galaxies tend to form in the densest clumps of dark matter, which naturally makes the universe look much more clustered compared to a smooth field of particles in various simulations. Additionally, the movements of galaxies towards some of these dense clusters creates something referred to as the redshift space distortion, which tends to visually stretch some of the structures along the line of sight. Or basically, it introduces an additional bias when it comes to redshift. And so when Sawala compared the DESI data to more realistic simulations such as the Flamingo simulation that we've discussed in some of the previous videos here in the description, the simulation that accounts for all of these biases, the mysterious signals suddenly were a perfect match for what we expect in the standard lambda CDM. Or in other words, that exotic explanation was no longer necessary. And though you might assume that this is some kind of a debunking process, in reality this is something much more important. Even though this was published in the Nature magazine that normally has a very strict peer review process, here this preprint study is a beautiful example of how science actually works. Because in this case, the original authors made all of their data and all of their code publicly available. So basically anyone can just go in, and if they know what they're doing, they can try to recreate the results and see if there's a mistake. This is once again science at work. And well, it took the collective eyes of the global community to catch such a mistake and to basically explain what's going on without breaking cosmology. And though I guess you could maybe criticize Nature for letting this paper being published, or even criticize the original authors for making this mistake, that's literally the opposite of what science is about. Instead, we should be focusing on the reinterpretation of data and celebrate the fact that here we can have a discussion about all of this and find the mistake, correct the mistake, and continue the scientific inquiry without anyone basically getting angry. And that's the power of the preprint system. Researchers very often post their work to servers like Archive, where I basically almost always get all of my studies, which then allow thousands of researchers to weigh in, find out what's going on, and possibly discover something in the process. But I guess in conclusion, so is the cosmological principle still safe? Yeah, looks like it is. Because looks like the local distribution of galaxies is not violated and is not unusual, and it looks like this paper from Nature might have just had a mistake. But it does not mean that the cosmological model is still perfect. As a matter of fact, we still have ideas like Hubble tension and a lot of other ideas we discussed in previous videos that still suggest something in the cosmological model is missing. Nobody can agree on what it is or how to solve this, but as of mid-2026, we know that there is something going on. It's just unlikely to be this. As a matter of fact, as we discussed in the previous video, that data from DESI even suggests that maybe the cosmological constant is not a constant, which would actually also create a bunch of problems. But the conclusion here is that the universe still remains quite mysterious and quite misunderstood. And while this particular challenge of the smoothness of the cosmos turned out to be a measuring mistake, it only means that we need to keep trying to answer these questions in some way or another. This was a great attempt, but unfortunately, it was based on a mistake. But as science often reminds us, sometimes being wrong just means that we're getting a little bit closer to being right. And so as scientists continue to analyze the data from DESI and additional surveys, we're slowly going to get closer and closer to that final answer of what the universe is actually doing. But at least for now, we're going to kind of end this at the mystery. We don't really know what's going on. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM it directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.